Now we're going to go over our second video on logic and set theory. So the first thing we're going to talk about are De Morgan's laws. And these might look a little bit complex to you, but let's go over what they actually mean. So as you see, it says not P and Q is equal to not P or not Q. So what does that really mean for us? Here's an example. So if P is the statement, I did my math homework, and Q is the statement, I did my reading homework, then P and Q would mean that both of those are true. So P and Q is, I did my math homework and I did my reading homework. The negation of this statement would be like the opposite of that, if you get what I'm saying. So I either didn't do my math homework or I didn't do my reading homework. So as you can see, the negation of P and Q is I didn't do my math homework or I didn't do my reading homework. Now, this statement right here is literally just not P, because not P would be I didn't do my math homework, like the negation of this, and not Q would be I didn't do my reading homework. So this statement right here is merely just equal to not P or not Q. So let me just write this, not P or not Q. So this is the first of De Morgan's laws. There's a second one as well, and it looks really, really similar. So here's the second one. So it says that the negation of P or Q is not P and not Q. So let's use the same statements, P and Q. I did my math homework. I did my reading homework. In this situation, P or Q would be I did my math homework or I did my reading homework. So what would the negation of that be? The negation would be that I didn't do either of them. So not P or Q is I didn't do my math homework and I didn't do my reading homework. Now we're going to see a few different types of very important laws. So first we have the identity laws, we have the domination laws, the idempotent laws, the double negation law, the commutative law, the associative law. We have some more laws on the next page, but let's just talk about a few important ones. So these ones up here are like kind of self-explanatory in a sense, but I would like to focus on this law right here, the double negation law. So it says the negation of a statement is equal to the original statement itself. So for example, let's say I have a statement like the sky is blue, then the negation of that statement would be the sky is not blue, and the negation of that statement would be the sky is blue. So as you can see, when I take like two negations in a row, like the negation just goes away, we get the original statement. Now let's look at the commutative laws. So these laws are also like pretty like obvious. So I'll give you like an analogy first off. So like, for example, when I have like two numbers, let's say like 5 and 2, and I want to add them, I'm going to get 7. Now, I can also do it the other way around, and I can do 2 plus 5, and I'll also get 7. So the actual order in which I add these numbers does not actually matter. So in the same way, if I'm using this AND operator between two statements, the order in which I write the statements doesn't actually matter. And the same thing for the OR operator. The order in which I write the two statements does not actually matter. All right, so now let's look at the associative laws. So basically, like for the associative laws, we have either and or we have or, but the idea is that the order in which we apply these operations does not matter. So again, this is with statements, but I'll just provide you an analogy with addition because I think that would like make the most sense for most of you. So for example, if I'm doing, let's just say like 1 plus 2 plus 3, like obviously the answer is 6, right? But I can do this in a few ways. Like I can either do it like this. I can do the 1 plus 2 first, and then I can add 3. And in this case, I would get 1 plus 2 is 3, and then I add 3 and I get 6. Or I can do it in this other way. I can do 1 plus 2 plus 3. So I can do this 2 plus 3 first, and I'd get 5. So this is just 1 plus 5, or 6. So like the order in which I add does not matter. And in the same way, as long as if I have the same operator, like the AND or operator, the order in which I perform those, like the order in which I perform either P and Q or Q and R, like that order does not matter at all. So this is the associative law. These are the associative laws. Okay, so now let's talk about the distributive law. So this is kind of like the distributive properties. So let's just go back to what the distributive property is from algebra. So if I have like 2 times 3 plus 5, for example, I could do this directly. I could say that that's like 2 times 8, and that's equal to 16. Or I can do this distribution. Like I can do it like 2 times 3 plus 2 times 5, and that's going to be equal to 6 plus 10. And I do get my same answer, 16. So if you see, the distributive law with statements is kind of like this distributive law. So P and Q or R, it's the same as doing P and Q or P and R. And the same law works in the other way. All right, so this is another very important law, De Morgan's law, De Morgan's laws. It says that if I'm negating a statement like P and Q, it's equal to not P or not Q. And if I'm negating the statement P or Q, it's equal to not P and not Q. And if you do recall from our slide above, we did talk about De Morgan's laws. So we talked about the second one here and then the first one here. All right, so now let's go ahead and look at 2 different code examples. So pretty much my claim is that these 2 code examples are equivalent. That means they do the exact same thing. Like, yes, I did write the code in a different way, but they will do the same thing. So before we even get to that, let's figure out what the problem is asking for. So let's just do that by looking at the first code example. So I have some number n, 10,000. I'm keeping track of some count, and I'm looking at numbers between 1 and 10,000. If you know Python syntax, this endpoint right here is exclusive. So it's from 1 to 10,000. So basically, like with all the numbers in that range, I'm seeing, okay, are they divisible by 0? That's one condition. Or are they divisible by, or like when you divide them by 5, do we get a remainder of 1? And when we divide them by 7, do we get a remainder of 1? So I'll give you like some examples of numbers which satisfy this second condition. So for example, like 1 is a number which satisfies the second condition right here, because when I do 1 divided by 5, that's going to be equal to 0 with a remainder of 1. And then when I do 1 divided by 7, that's going to be 0 with a remainder of 1. Now, another example of this number is 36, because when I do 36 divided by 5, I get 7 with a remainder of 1. And then when I do 36 divided by 7, I get 5 with a remainder of 1. So both of these are like 2 examples. Now we also need to meet the second condition. We need to meet the second condition that the number is also divisible by 3. So 1 doesn't actually work for us because 1 is not divisible by 3. But 36 does work for us because 36 is divisible by 3. And of course, it satisfies the second condition, which is how we got it. But the basic idea is like, okay, we have some condition, right? How many numbers inside of our range are going to satisfy that condition? We're keeping account of those. Now, I'm going to basically rewrite this statement a little bit with the distributive law. So what does the distributive law say again? It says that like P or Q and R is equal to P or Q and Q or R. Okay, so let's go ahead and maybe for simplicity, we'll just like call this statement right here P. And then we'll call this statement Q and we'll call this statement R. That means up top we have P or Q and R. Right? We have P or Q and R. Now, this should be equal to the following based on the distributive law. It should be equal to P or Q and P or R. And notice that's exactly what we wrote here. And notice that's exactly what we wrote here. We wrote I, like this is P, right? And this one is Q. So we wrote P or Q, and we wrote P or R. So at least according to what I mentioned to you earlier, these should be the same. But maybe you're a little bit skeptical, which, I mean, it's reasonable. So let's just see if they're actually the same or not. All right, so I'm going to write the code the first way. So again, my integer n is 10,000. I'm keeping track of a count. Okay. Now I'm going through the numbers from 1 and then n plus 1. And if my number is a multiple of 3, and whenever I divide my number by 5, I get 1. By the way, this should be an OR. And whenever I divide I by 7, I get 1. Then I meet my condition. Then I'll just like increment my count. So let's just print out the value for my count. Okay, we have to use 2 equals. All right, so we get 3, 5, 2, 4. So if we rewrite this statement a little bit, we should get the same, like we should get the same answer. So let's go ahead and comment this part of code out, and let's just rewrite that statement. All right, so if I rerun this, I should get the same answer. So let's see. And I do get the same answer. So as we can see, we can like rewrite statements, and we can rewrite them in equivalent ways. And oftentimes, for different code examples, writing something one way or another will be easier or harder. But you don't have to worry about like, okay, is this actually correct or not? Because you know mathematically that they're equivalent to each other.